Hello! So here we have our first educational video on our chemistry topic, and today we're going to be discussing measurements.
I'm here to work the whiteboard. I'll be doing things on the whiteboard.
So whenever I'm talking, Lucas will be hitting you up with some wonderful examples, and I'll be trying to cover the topics as efficiently and thoroughly as we can. So here we go. The first thing that we need to talk about with measurements is qualitative versus quantitative data. So when you're looking at qualitative data, that's stuff where you're having observations. For example, if you're doing an experiment and you're looking at the ocean every day, you say, the ocean looks very blue today versus the ocean looks kind of green today, or the ocean looks pretty brown today. That's qualitative. It's observations when you're saying something, describing using words. Now on the other hand, quantitative data, which is the other type, is when you're using numbers to describe something. That's using the measurements. And we're going to be focusing mostly on quantitative data today. And that's when you're talking about your measurements. Say you're measuring the temperature of a substance, or maybe you're going to be measuring the heat released, you're going to be measuring the size of something, the length of something, or a time that's gone by. And anytime you have a number, you're saying quantitative. And those are the ones where you really have to watch out for error. So when you're looking at uncertainty in quantitative data, there's always going to be some degree of uncertainty. However, it be very small. For example, if you have an electron microscope, you can get down to these tiny levels of uncertainty. However, at the same time, in a high school laboratory, you'll often have very large amounts of uncertainty. Either way, you have to know how to quantify it and use it effectively. So when you're talking about uncertainties, they tend to come from two different sources, and those would be random and systematic errors. Random errors is when your uncertainties is coming from uncertainties related to your instruments that you're using. For example, if you're using a standard ruler, it's only going to go down to the millimeter. So anything that's beyond a millimeter is going to start being uncertain. Now, when we're looking at this, you have your analog and your digital within your random errors. Your analog errors are going to be with analog instruments, which is anything like a ruler, a meter stick, or a thermometer that you're looking at, a traditional thermometer, mind you. And these are the ones where you're reading off the measurements, versus digital instruments are the ones where you're looking at it and it'll have a literal digital readout where it's telling you what's going on. With analog, what you do is you take the smallest increment, and it's going to be half of that for either end you're measuring it on. So, say if you're measuring with a thermometer, which is only going to have 1 point to measure on, you're going to have, and it goes down to the smallest degree, you're going to have half of a degree being your uncertainty. Keep in mind, however, if you're measuring with something like a ruler, you're measuring two ends. So you have, at your one end, you have your 0, which you're going to be plus or minus a little bit on, and you're going to have your end where you actually think you're measuring. So in that case, you're going to want to make sure to double your uncertainty, and in that case, it'll be the smallest measurement there. So for a ruler, it would be an uncertainty of plus or minus 1 millimeter typically. Now, for digital, you're going to be looking at a much simpler process. All you have to do is look at your digital instrument, look at the smallest level that it goes to. So if you have a digital scale that reads to the centigram, then your uncertainty is going to go to the centigram. It's going to be plus or minus 1 centigram. That's all you need to know. So if your scale reads out 32.04, then your uncertainty is going to be plus or minus 0.01. That pretty much covers it for your random errors. And these ones can be reduced by multiple trials, because over time you can get more and more accurate and get a better picture of what you're looking at. So these ones can be reduced by multiple trials. However, they can't be eliminated, even though you can still reduce them also by getting better instruments. The next type of error can be eliminated, and these are going to be your systematic errors. Systematic errors are whenever you screw something up. It's to be human error. Maybe you accidentally put in twice as much sulfuric acid as you meant to. Not a good idea. Or perhaps what you did was you dropped the ball way too fast. Or you forgot the fact that some heat's going to be escaping from your experiment. Either way, these really aren't the ones that these ones are eliminatable. So by improving your procedures and by looking at what you're doing and saying, I can improve this, then you can go back into your lab recreate the lab, and typically you can get rid of the majority of systematic errors. That being said, when you're writing up a lab report, make sure you don't put down the systematic errors were one of the reasons why you screwed up in your conclusion. Because you know what your professor will say? He'll say, "Oh darn, why didn't you redo your lab then?" And you won't get too great of a grade. Just keep that in mind. Next up, we're going to be talking about sig figs, which is short for significant figures. Significant figures are what you're going to be looking at whenever you're looking at a measurement, and it's going to tell you how accurate that measurement is. Now, significant figures follow a few rules. Say you have a number which is 1,220, and it doesn't have a decimal point at the end of it. Because there's zeros following it, it's only going to have 3 significant figures, because any integer is going to automatically be part of the significant figure counts. So the ones that aren't part, you're going to see you have zeros. If a zero is in the middle of integers, like 102, it's going to be 3 significant figures. However, if you see a zero in front of the integers, like 102, you can axe that one, it's still going to be just 3 significant figures. Also, if you have a zero following your number, but that zero itself is not followed by a decimal point, it's also going to be to the number of significant figures indicated by your integers. For example, 3,200, if there's not a decimal point at the end of that, you're going to be looking at 2 significant figures. Drop a decimal point at the end of 3,200 point, and at that point you'll have 4 significant figures, because it's indicating that it's accurate to the ones place. Finally, if you're looking at any decimals, you're going to be looking for zeros for your significant figures that precede the number. For example, 0.002 is going to have 3 significant figures. The first zero before the decimal point isn't going to count because it's a leading zero. However, when you're looking at zeros between the decimal point and the integers, those will always be significant, whether they're on the side to the left of the decimal point or to the right of the decimal point. So whether it's 0.002 or 200 point, it's still going to be 3 significant figures. Watch out though, because if you have trailing zeros, as in 0.00200, then those zeros are also going to be significant, because those are there to indicate that it's significant to a further place. That's about it for significant figures, so just keep an eye out for them, because whenever you're going to be performing calculations in chemistry, you're going to want to keep them regular, and we're going to go back in a little while and talk about how to add and subtract, as well as multiply and divide with significant figures. But first we're going to go into a little offshoot and talk about accuracy and precision. Accuracy and precision are fairly simple concepts, but they're really easy to confuse. All it means, accuracy has a low error, and the error is how far away your experimental value is from the theoretical value, or the value that's known to be correct. So if that error is, you're saying it's accurate, or if your results are going to be accurate, they're going to be very close to what you thought you were going to get. For example, if you listed your atomic mass of carbon as being 12, and of course the atomic mass of carbon is actually 12.01, that would be a very accurate result. On the other hand, precision discusses the idea of your results all coming within a close range of each other. It's kind of like if you're on a shooting range and you drop all your shots through the same hole, except for those shots are all on the outside of the target. So they're inaccurate, yes, but at the same time you have replicability throughout your experiment. With that replicability, that indicates it's going to be a systematic error instead of a random error, because your device was perfectly accurate enough to get similar results again and again. However, because your mark was way off and your experimental results are consistently inaccurate, you probably have something wrong in your procedures. Think systematic. Next up, we're going to look into quantifying uncertainties. So with uncertainties, you're going to have 2 different types of uncertainties. You're going to have uncertainties that come in integer values, as in 20 plus or minus 2, but then you also have uncertainties that come in percentage values, such as 20 plus or minus 4%. And for these, they're going to be about the same for both uncertainty and percent error. All percent uncertainty means is how much you're unsure about something. That's going to be your plus or minus value. With percent uncertainty, for example, you're going to see for the number 4,224, if you have the percent uncertainty plus or minus 5%, to find out your integer uncertainty, all you have to do is multiply your number by that 5%, and it'll give you what number plus or minus you're expecting for this measurement. Keep in mind that uncertainties will only ever be to one significant figure, because you can't be more certain about your uncertainty than you're certain about your original number. So when you're looking at uncertainties, you'll never have an uncertainty that's, say, plus or minus 4.024. However, you might want to keep these uncertainties with the certain number of significant figures they have until you're done calculating your final uncertainty, at which point you can round it to a single significant figure. In this way, it allows you to make sure that your uncertainty is accurate throughout the entire measurement. Converting from integer uncertainties back into percent uncertainties is just as easy. All you have to do is put your integer uncertainty over your total value and multiply by 100, and at that point, what you've got yourself is a percent uncertainty. Slap the percentage sign right on there, and you'll be good to go. Now, once you have these wonderful uncertainties, whether they be percent or integer, you'll need to know what times you use them. So when you're adding or subtracting, make sure you have your integer uncertainty rocking. That being said, remember, if you're adding two things, you're not going to be dealing with percentages, because that deals with the total value of something. Instead, you want to deal with just how off it is, which is going to be your integer uncertainty. Now, when you're multiplying or subtracting, you're going to want to convert your uncertainties from integer uncertainties into percent uncertainties. And then, once you've converted them there, all you have to do is complete your equation, and then you're going to be adding or subtracting, depending on whether it's multiplication or division, your percent and your percent uncertainties. Finally, the same is going to hold true for any exponent, in which case you're going to stick with your percent uncertainties and use those to complete the expression. So for example, if you have 5 plus or minus 0.01, and you want to take that to the second power, what you'll do is first you'll have to convert the 0.01, because it's an integer uncertainty, into a percent uncertainty, which means you have to put 0.01 over 5, and then once you put 0.01 over 5, you multiply that by 100, and that'll give you a nice clean number. Once you have that percent uncertainty, then you just have to square your 5, because that's your main expression. That'll give you your 25, and then your percent uncertainty, you're going to multiply that by 2. And because remember, when you're looking at these expressions, they drop down one in the order of expressions. So when you're looking at your multiplication and division, it's going to be adding. And then when you're looking at your exponents, so when something's squared, then your percent uncertainties are only going to be multiplied. That covers it for percent uncertainties. And then when you're looking at sig figs, it's going to be a similar deal. When you're talking about your sig figs, you're not going to have to worry about your significant figures when you're going to be adding and subtracting. You only have to keep them to a consistent number of decimal places. However, keep in mind when you're multiplying or dividing, you'll want to make sure that your significant figures remain the same. Which means if I multiply 2 by 24, the final significant figures should only have the final expression should only have a single significant figure, because 2 has one significant figure and 24 has 2. And that about covers it.